Never before has a man-made object come so close to the Sun. The Parker Solar Probe will provide unique measurements about our star. But for all the excitement about this project, people are left with one question. Why doesn't the probe melt when it's near the Sun? The Parker Solar Probe periodically stays in the hottest layer of the Sun, but this is not the surface of the Sun. The hottest part of the Sun is a corona, which surrounds the Sun. In this video, you will learn how the solar probe withstands the intense heat and what new insights it will provide. Before we begin, we would like to ask for your support on our channel. Please leave us a comment at the end that fits the topic. From now on, we will always reward our subscribers' contributions with a heart, and we will pin informative and enriching comments at the top so that everyone reads them first. Just make sure you're subscribed, like the video, and mention both in your comment. The journey to the Sun. Exploring our star is of utmost importance to us Earthlings. Without the Sun, there would be no life on our planet. Our climate and seasons depend on solar radiation. The Sun's activities also constantly influence the magnetic field of our planet, and some people even claim that solar storms have similar confusing influences on the human psyche as a full moon. From a purely scientific perspective, astronomers and cosmologists especially want to learn more about the mysterious processes on the surface of the Sun and its corona. Corona means crown, and it refers to the thin, glowing layer around the Sun. This can only be seen from Earth with special filters or during a solar eclipse. The corona remains a great mystery for scientists to this day. After all, temperatures of up to 1 million degrees Celsius prevail in this layer, which is located several kilometers above the surface of the Sun, while temperatures on the surface of the Sun are only about 6,000 degrees Celsius. Just like the Sun itself, the corona is not uniformly hot. Constant merges take place, with things bubbling up and forces circulating. It's similar in the corona, but there, the heat is in the form of fine particle clouds. These clouds, or evaporations, are directly influenced by the activities on the surface of the Sun. The particles that form the corona are created by fiery processes on the Sun or at least influenced by them. These interactions are not yet fully understood, and one of the Parker Solar Probe's tasks is to uncover more about these connections. Behind the extreme heat formations around the Sun, there must be physical forces and probably also chemical processes that we do not yet know of. Perhaps we could even benefit from the probe's findings regarding our own energy industry. Just think, the electricity you draw from a wall socket is generated by heat. If we were able to generate temperatures or heat using the same process that the Sun uses, we might be able to generate large amounts of energy much more easily or multiply energy in a simpler and more ecological way. In addition to studying the enormous heat in the corona, the probe is also measuring the famous solar storms. These are gigantic particle eruptions, and the winds originate from violent eruptions on the Sun's surface. During these eruptions, plasma and particle streams are released, which initially waft around in the immediate vicinity of the Sun. Eventually, these charges also enter the corona and are released from the Sun's gravitational pull by a mechanism that is still largely unknown. These particle streams then drift away from the Sun at extreme speeds and out into space. If these particle streams meet the magnetic field of the Earth, they can severely distort it. Experts believe that such solar winds, if strong enough, could disrupt electricity on Earth. Solar flares and winds have been intensively researched for almost 100 years. This research has been enough to identify certain patterns in the eruptions and winds. The Sun usually follows an 11-year cycle, with eruptions occurring in certain patterns. The winds could be predicted for a certain period. But then, suddenly, the behavior of the Sun changed. First, its activity weakened in an unusual way, causing concern. Then, unexpectedly, solar activity increased again. These events occurred completely outside the known cycles, leading scientists to worry. We cannot be sure if the Sun will exhibit extreme changes in behavior from time to time, and this could pose dangers for our increasingly technical world. It is crucial that we learn more about the Sun. A total loss of electricity could plunge the planet into indescribable chaos within hours. So, the Parker Solar Probe plays an enormously important scientific role in many ways. The Parker Solar Probe. Launched in August 2018, the Parker Solar Probe is a joint project between NASA, ESA, and several other nations. NASA took advantage of a window of time when the Sun and Earth were particularly close, making the probe's trajectory ideal. Since probes cannot head straight for their destinations, they move along the gravitational fields of planets and use their force for further flight. The Parker Solar Probe first made 7 flybys of Venus before it could set course for the Sun. NASA also used these flybys of Venus to gather new impressions of Venus itself. In April 2021, the time had come. The probe flew through the glowing hot corona of the Sun for the first time. The probe came within 6.1 million kilometers of the Sun's surface, despite temperatures outside reaching 2,500 degrees Celsius. Inside the probe, the sensitive measuring instrument stayed at just over 30 degrees Celsius. International teams of scientists, engineers, and technicians spent nearly 10 years designing this masterpiece. The key to the probe's success is a sophisticated thermal protection system, which includes special materials, a heat shield, the probe's position, and a water-powered cooling system. The Johns Hopkins Applied Physics Laboratory in Maryland, USA, was responsible for building the water cooling system. The thermal protection system has 2 layers of carbon fiber reinforced carbon, which retains its structural properties even at the highest temperatures. In between these layers, there is carbon foam that has large air pockets, preventing heat transfer to the outside. The Parker Solar Probe is completely encased in white aluminum oxide. The color and material reflect light optimally, so the outer covering reflects more heat than it absorbs. Between the carbon and aluminum oxide layers is a tungsten layer. This dense metal only boils at a heat of 5,900 degrees Celsius. Due to this tungsten layer, the outer skin and the carbon layers inside the probe practically cannot react with each other. The heat stays outside even under the extreme conditions in the Sun's corona. The probe's position and trajectory are programmed to always keep the shield facing the Sun. To ensure that the Parker Solar Probe can still look directly at the Sun, cameras and measurement sensors are placed just behind the protective shields, barely peeking out. During its flight through the outer corona, the probe will only pass through the outer layers for a very limited time. In these outer layers, the amount of hot particles the probe encounters is very small, so the heat transfer remains at a tolerable minimum. You can roughly compare the flight of the probe through these extreme temperatures to reaching into a hot oven. As long as you don't touch any metals or heated food, you won't get burned. If your hand stays in the oven for only a short time, the heat doesn't affect you much. The Parker Solar Probe's flight times are specifically designed to limit its exposure to extreme heat. Although the probe was perfectly equipped, the scientists and engineers held their breath during the first pass. When the Parker Solar Probe remained fully functional on April 28, 2021, even at temperatures approaching 3,000 degrees Celsius, there was great joy among NASA and all other facilities involved. The probe traveled at speeds of 586,000 kilometers per hour, briefly racing through the Sun's corona.